The following program is intended for the purposes of education and harm reduction. I am not a medical professional, nor do I ever intend to become one. I am only a concerned citizen whose independent research in response to events within my private life has uncovered information which may interest others as much as it has interested me. Do note that taking psychiatric medication improperly can be dangerous and even fatal. I encourage you to seek out the advice of a trusted medical professional before making any changes to your behavior in response to the material outlined in this presentation. I brought you here today to talk about a topic that's very close to my heart. A topic that has been on my mind for a long time now. A topic that gets a lot of attention, yet never seems to get the attention it deserves. Antidepressants.
We'll see a psychiatrist, don't be afraid. We'll see a psychiatrist, don't be afraid. We'll see a psychiatrist, don't be afraid. There is no escape to play.
Antidepressants are a funny sort of thing. Pharmacological drugs are each designed to be a magic bullet of sorts. First, something that causes a disease is identified, usually a virus, bacterium, or fungus. It is then mankind's job to design a substance that can be absorbed by the body and somehow disable that disease-causing agent while leaving the rest of the body intact. Antidepressants are designed to be magic bullets that target emotions, not something physical like a virus, bacterium, or fungus. How can we possibly create a substance to neutralize something we can't see under a microscope or measure in any reliable way? Before we start trying to figure out the how, there is something else we should go over. The creation of the very first antidepressant. Since the beginning of civilization, humans have spent a lot of time thinking about the nature of depression. People's thoughts about depression have led to many, many ideas about the best way to let go of their darkness and feel happy in their lives. The birth of modern antidepressant drugs, however, stretches back only to around the 1950s. It was the result of many studies all taking place at once. To keep things brief, let's focus on only one small slice of this research related to iproniazid. Iproniazid is a drug created with the intention of treating patients suffering from tuberculosis, a bacterial infection of the lungs. It began to be seriously studied in the early 1950s, And though it did prove to be an effective treatment for tuberculosis, side effects were quite common, so it was abandoned in favor of other medications. Though, these side effects ended up being quite interesting. Researchers noticed that when patients with tuberculosis who were suffering from depression started taking this drug, their mood noticeably improved. This was fascinating. Many studies began to be performed on the antidepressant effects of iproniazid and other drugs used to treat tuberculosis. Some think that it is during this time that the term antidepressant was first coined by Max Lurie, a psychiatrist with a private practice in Cincinnati. He used it to describe the effects of isoniazid, another medication originally used to treat tuberculosis. In 1957, psychiatrists Nathan S. Klein, Harry P. Loomer, and John C. Saunders of Rockland State Hospital in Orangeburg, New York, were the first to present results assessing the effectiveness of iproniazid in depressed patients who were not suffering from tuberculosis. And just one short year later, more than 400,000 patients suffering from depression would be the first to be treated with the first class of antidepressants to ever hit the market. 0 to 400,000 patients in just 1 year. An explosive growth rate for a very new type of drug that was documented as having pronounced and frequent side effects. A drug known for causing liver damage to the point of death in studies of its effectiveness as an antidepressant. Not all that surprising, given the state of psychiatric research in the 1950s. There were no written rules or laws outlining the limits of experimentation on the mentally ill. There was no process for consent. Psychiatrists could perform just about any experiment they wished on living subjects and suffered no consequences if their patients ended up dead. In 1939, 90% of all admissions to state and county hospitals in the United States were involuntary and required only 2 physicians' signatures for admission. We're talking about an era in which ice pick lobotomies were considered valid treatment options for the mentally sick. Hey, do you want to take a deeper look into the mind of Nathan S. Klein? Smart folks have pretty wild ideas from time to time. Klein had visions of a future where humans live as literal cyborgs. Klein truly believed that we can mold the human body to suit the will of man. Given the context and the time in which he worked, I can't help but find this at least slightly concerning.
So here we have cyborgs and space, altering man's bodily functions to meet the requirements of extraterrestrial environments would be more logical than providing an earthly environment for him in space. Of course, written by Kleins and Klein. You gotta watch out for these Klein folks. And what I was most interested to discover in this article is that cyborgs have already come to fruition, even in this time period. We have here one of the first cyborgs. This 220-gram rat has under its skin the Rose osmotic pump, which is this thing right here. You get a better look of it, like this. Designed to permit continuous injections of chemicals at a slow, controlled rate into an organism without any attention on part of the organism. This rat has nothing to worry about. All these chemicals are delivered, they're all fine. And way more logical than, having an earthly terrarium to put around the rat to keep it alive. Yeah.
But enough about cyborgs. Let's get into the how of how iproniazid and other antidepressants actually work. You're probably familiar with the monoamine hypothesis of depression. It's sometimes referred to as the chemical imbalance theory in order to appeal to us non-neuroscientists. The simple explanation of the theory is that the brain contains many chemicals. If you're depressed, it's because the chemicals in your brain are not in the right proportions. They're imbalanced. Perhaps you're missing some chemicals, and drugs could deliver these chemicals to your head. The name monoamine hypothesis goes a little more into detail about the types of chemicals that are supposedly not balanced, monoamines. But what is a monoamine? Before we get to that, the brain is home to a special kind of cell called a neuron. And a neuron looks something like this. Of course, here, very cartoony version with a deep cutaway. But you still get the gist. You have this cell, it's got a body and a tail. This tail here is called the axon. You'll notice these long spindly bits coming out of both the body and the axon. We got the long spindly bits here. These are called the dendrites of the neuron. The long spindly bits at the end of the tail are the axon terminals. Our brains each contain billions of these neurons, and each neuron is connected on average to 1,000 other neurons. Neurons connect where the axon terminals of one neuron meet the dendrites of another. Here, let me show you a more comic book style image of what that actually looks like. You can see you have neuron 1 here, neuron 2 here. Here's that axon thing, or the tail, coming out of the neuron and connecting from the axon terminals to the dendrites of neuron 2. And here's a close-up of that connection. You'll notice that the two neurons never actually touch and are always separated by a tiny gap referred to as the synapse. Neuron cells are able to communicate with each other. Communication between neurons is thought to be involved in the way our brains think. We don't understand exactly how thinking works, but we have reason to believe that the acts of thinking and feeling are tied to the activity between neurons. We have studied the activity of neurons in response to certain events. For example, the event of seeing a new object versus an object we haven't seen before. If someone is shown an object they have never seen before, it will cause a surge in activity in a patch of neurons in their brain. When they are shown that object a second time, those same neurons do not respond as strongly. The act of being introduced to an object and memorizing its features involves a change in the way our neurons interact. We also observe extreme effects on thinking and feeling when neurons get damaged due to physical damage or from diseases such as Alzheimer's that cause the death of neurons. Neurons communicate by sending electrical signals through their bodies in order to send chemical signals to the neurons they are connected to. These electric signals are called action potentials. Let me show you how they work.
Let's take a moment to try and remember some high school chemistry. Action potentials work by the neuron's clever use of ions. Recall that an ion is an atom that has a positive or negative charge. Positively charged ions are missing electrons, while negatively charged ions have extra electrons. A resting neuron is not really resting at all. You can think of a neuron as a boat with leaks in it, and positively charged ions are the water. Just like the crew of a ship wants the inside of their boat dry, a neuron wants to keep its insides mostly negative. Here we have an oversimplified model of a neuron. Nothing here is made to scale, but this model should give you an idea of the flow of particles in and around neurons. The inside of a neuron contains many things, but as far as action potentials are concerned, know that it contains some various negatively charged molecules and some positively charged potassium ions. The neuron is surrounded by positively charged potassium ions as well as positively charged sodium ions. The potassium ions pass into and out of the cell through holes called channels relatively freely. These channels are picky and will only let in potassium ions, not sodium ions. The sodium would like to pass into the neuron through the neuron's sodium ion channels, but these are closed, and if a sodium ion does happen to make it into the cell, like water into a leaky ship, it is pumped out. This has the effect of keeping the inside of the neuron mostly negative. A chemical signal at the synapse from a nearby neuron tells the neuron that it's time for an action potential. This signal tells sodium ion channels near the synapse to open up, which is the equivalent of putting a big hole in the ship. With sodium channels open, sodium ions flood into the neuron, and the small negative charge inside the cell is disrupted by the inflow of positively charged ions. This shift in charge acts like another signal that instructs nearby sodium ion channels to open. This causes a chain reaction that will push the shift in charge all the way through the neuron. After sodium ions flood in, the crew of the ship gets right to work, and all of the positively charged sodium ions are pumped out of the neuron to restore the balance from before. The sodium ion channels are closed up, and they will not reopen for a short waiting period. This keeps the flow of ions moving in one direction. The action potential is carried all the way down the neuron, but when it reaches the end, it doesn't just zap its neighboring neurons. The end of the road is the synapse, the place where one neuron meets another, and these synapses have other channels that allow another special ion into the neuron, a calcium ion. There are structures at the synapse called synaptic vesicles, which are basically bags of neurotransmitters. The calcium ions do something that we don't quite understand that allows these bags of neurotransmitters to fuse to the outside of the cell, releasing the neurotransmitters into the synapse where they will travel to the other neuron and bind to it. But what is a neurotransmitter? It's simply a chemical that's stored in a neuron that is released into the synapse to trigger a reaction in a neighboring neuron. Neurotransmitters are very diverse and serve a variety of different functions. As many as 50 different substances may be released at synapses in the brain. When they are released, they will generally bind to a receptor on the other neuron designed to receive that specific neurotransmitter. When these neurotransmitters bind to receptors, it begins a domino effect of chemical changes within the other neuron. Some of these chemical changes trigger action potentials, and others make it much harder for a neuron to go through an action potential. Over time, the neurotransmitters that are in the synapse and causing all of these changes will be removed. They will either be carried back into the neuron that released them, or destroyed by enzymes, a protein that causes chemical reactions to happen much faster than they regularly would. In this case, they speed up the breakdown of the neurotransmitter. There's a special type of neurotransmitter called a neuromodulator. These chemicals bind to special types of receptors and have a wide range of effects. They have the power to turn genes within the nucleus of the cell on or off. They have the power to shut down and start up the enzymes that help the cell with protein creation. And of course, they can alter the behavior of the ion channels.
They can control how sensitive an ion channel is in response to the neurotransmitter, how long an ion channel stays open during an action potential, and even what kinds of ions it lets in. These neuromodulators can do a whole lot, and thus seem to be involved with a large amount of mental and bodily functions. Monoamines are basically just a set of neuromodulators that are made from amino acids. The main monoamines thought to be involved in brain function are dopamine, epinephrine, norepinephrine, and serotonin. And there you have it, the root of the monoamine hypothesis of depression. In summary, monoamines are just neuromodulators, chemicals that the cells of our brain shoot at one another in order to make changes to each other. Sounds like it would be involved in controlling the way we feel, but how exactly did we come up with this hypothesis? There's a lot that led to this theory, and like most out there theories that humans have come up with, it all starts out with LSD. In the 1950s, the behavioral effects of LSD were well known, and it was noted that LSD had the ability to block serotonin receptors from receiving serotonin. Thus, maybe it was a lack of serotonin that caused the behavioral effects of LSD. There's also Reserpin, a medication used to treat high blood pressure. Reserpin allegedly had a tendency to make its users feel more depressed than usual, and it was also noted that Reserpin interfered with the brain's ability to store the monoamines serotonin and norepinephrine. And then there's our old friend iproniazine. This drug was discovered to have the ability to shut down enzymes called monoamine oxidases, or MAOs. You can think of the monoamine oxidases as monoamine killers. When monoamines are released into the synapse to act as neuromodulators, it's often the case that a monoamine oxidase enzyme will swoop in at just the right time to break down the monoamine and stop its effects. Since iproniazine was killing the monoamine killers, and it seemed to make people happier, there's just more evidence in favor of the hypothesis that more monoamines in the brain help depressed patients. Sounds convincing, but of course, there's more to the story. The monoamine hypothesis of depression has come under fire many a time. For one, it is common to all antidepressant drugs that it takes around 2 to 3 weeks before the antidepressant effect becomes apparent. But the change in monoamine levels in the brain as a result of taking antidepressants is often happening within the first few hours of the first dose. If depression was solely due to low monoamine levels, this 2-week delay shouldn't happen. Further, we know that drugs like cocaine and amphetamines increase levels of serotonin, but seem to have no effect in treating depression, at least in the long run. The list goes on. I mentioned earlier some studies suggesting that the drug Reserpin caused depression by lowering monoamine levels. Well, it turns out there's also a lot of research done to suggest that not only does Reserpin not cause depression, but it may even have an antidepressant effect. Many attempts to reduce serotonin have failed to trigger depression in non-depressed people. This is a hard theory to test, because it's currently impossible to directly measure serotonin levels in a living human brain. The serotonin system in the brain is immensely complex. Neurons covering all brain regions make use of serotonin-based signals, acting on at least 15 different kinds of serotonin receptors. not to mention the variety of different ways that neurons both create and destroy serotonin. Serotonin is obviously a big deal, but short of pulling out someone's brain and feeding it through a meat grinder, there's not much that can be done to keep track of it. Alright. I think we're set. I think you're ready to finally learn how antidepressants work. I will focus on a single antidepressant, one that has affected my life fairly severely, the drug that ultimately inspired this whole presentation. Cymbalta. I understand that there are many antidepressants out there, and you may be interested in a particular one. Currently, most antidepressants work in similar ways. Learning one will help you to understand the others, and I will do my best to teach you how to do your own research. If you're interested in learning about a drug that has been approved for use in the United States, a crucial resource is FDA.gov, the official website of the United States Food and Drug Administration. Thanks to the Freedom of Information Act, you can find a great deal of information about drugs that drug manufacturers are required to provide to the public. Let's go on a little tour here on FDA.gov and try to find those documents. So we go to scroll down here. There's a bunch of stuff about coronavirus, but we're interested in drugs. So let's click on that. All right, drugs. Here's the drugs section. You have a bunch of different stuff here. I'm not exactly sure what you'll find in these places, but drug approvals and databases. That's where you're going to want to go next. And you see they make it really easy to figure out, where to go to find these Freedom of Information Act documents. It's, clearly you click on drugs at FDA search. That's where you go. And all right, drugs at FDA. All right, Cymbalta. Cymbalta. Let's search. Cymbalta. Here it is. Notice when I click on it, I get 4 Cymbaltas. What does that mean? I thought there was only one Cymbalta. They all look the same, except for this one number here. NDA 021427, 021733, 022148, 022516. What's going on here? Well, to explain that, it helps to know a little bit about how drugs get approved for use in the USA. The FDA gives us a handy chart outlining that process. Here, let's zoom in a bit. All right, so we start here with the drug being developed. So, when a drug sponsor, which is usually the manufacturer of the drug, develops a potential drug, they must seek approval from the FDA to start producing it with the intent to medicate people. At this point, it is likely that the sponsor will get a patent on this substance. A patent is a property right on an idea. In the context of a drug, a patent gives the sponsor the right to exclude anyone else from making, using, offering, or selling the substance for a period of 20 years. 20 years from the patent application, that is. While there are obvious potential flaws in the system, giving single sponsors 20-year monopolies on potentially life-saving medications, perhaps, it's also necessary to have some sort of system in place like this in the pharmaceutical industry. After all, Much of the value of a drug comes from the massive investments in research and tests to ensure its safety. The production of the chemical itself is comparatively very easy, and we don't want a sponsor to invest billions of dollars investigating a new substance only for a bunch of no-name chemical manufacturers to steal their formula and reap all of the profit that would otherwise go to the sponsor making the initial investment. You heard me right when I said billions of dollars. It's realistic for it to take over $2 billion to get a new drug from the laboratory onto pharmacy shelves. On top of that, the drug development and approval process can take around 12 to 15 years. So basically, as soon as a sponsor gets a patent on a drug, it's a mad dash to get that drug approved so that you can get it out on the market and start making back some of that money before your 20-year window is up. So, a promising potential drug is made, and its patent is filed. What's next? First, the sponsor has to prove that the drug is safe. The sponsor will start by performing tests where the drug is given in various dosages to various animals. If most animals aren't killed by the drug, making the drug look reasonably safe, the sponsor submits an investigational new drug application, or an IND, to the FDA. This will be a report including the drug's composition, the results of animal testing, and the sponsor's plans to begin testing the drug on actual human beings. The FDA will then review the IND application. If they believe that there's enough information in the application to prove that the drug is reasonably safe to test on humans, the sponsor will begin to perform clinical trials. Clinical trials are tests of the drug on humans, and they are conducted in a few phases. In phase 1, the drug will be given to around 20 to 80 healthy volunteers. This is mostly to determine the side effects and study how the drug is absorbed in the human body. Animals give somewhat of an idea, but there's no species of animal that processes a drug in quite the same way that a human body does. In phase 2, the idea is to measure the effectiveness of the drug. The drug is now given to some hundreds of individuals affected with the disease that the drug is supposed to cure. Researchers will generally give some of these patients the drug and others what's called a placebo. A placebo is a pill that does nothing, perhaps nothing more than a capsule filled with a small dose of sugar. Participants in the trial take what's given to them, not knowing if the pill they get is the actual drug or the placebo. Each group of patients is then analyzed to determine how much better they're doing. If the group taking the actual drug is feeling much better than the group taking the placebo, then the conclusion is that the drug is effective. The reason some people have to take the sugar pill is due to a miracle of the human body called the placebo effect. Generally, when a person is not feeling good, an expectation of feeling better alone will actually make them feel better. It's a case of expectation becoming reality. You can think of the placebo effect as a sort of psychic opiate. And some research even suggests that the feel-good effects of a placebo pill result from the same pathways in the brain that true opiates affect. In short, having a group of people take the sugar pill and feel the full placebo effect gives you a group of people feeling as good as their body could possibly let them without actual treatment. A good group to compare against in studies like these. Phase 3 clinical trials and beyond are similar to Phase 2, just bigger with patient counts in the thousands. Trials can also be more varied, perhaps including trials where drugs are mixed, for example. So, when clinical trials are complete, the sponsor will meet with the FDA and then submit a new drug application, or NDA. Remember those NDA numbers from before? An NDA contains thousands of pages outlining the research done on the drug and is the official request to the FDA for US approval. The FDA reviews the NDA, and if everything looks legit, the FDA will create a drug label to package with the drug, containing all clinical information needed to safely use the drug. Holy smokes! That's a lot to go through to get your billions of dollars of research into the hands of consumers. The review of the thousands of pages in the NDA obviously takes a long time, but did you know that there's a shortcut? Since 1992, the Prescription Drug User Fee Act allows sponsors to pay the FDA some extra money to have the drug approval process sped up. I'll say it again. Sponsors can pay the FDA directly to have their drug out on the market faster, thus generating profit faster. I don't see how this process can be exploited at all. The 4 Cymbaltas represent the 4 NDAs submitted to the FDA. Recall that Cymbalta was designed to be an antidepressant, and if you look at the first NDA's label, and we go to indications and usage, there it is, you see that Cymbalta is indicated for the treatment of major depressive disorder. Makes sense. How about the next NDA? Here's the label from that. Major depressive disorder and diabetic peripheral neuropathic pain. Alright, how about the next one? The next NDA looks a little different. Major depressive disorder, generalized anxiety disorder, diabetic peripheral neuropathic pain, and fibromyalgia. What about the next one? The last NDA to be submitted to the FDA results in this label, and this says that we can use Cymbalta to treat major depressive disorder, generalized anxiety disorder, diabetic peripheral neuropathic pain, fibromyalgia, and chronic musculoskeletal pain. It must be a miracle drug, huh? Or maybe making drugs is expensive, and to make back the money that goes into the research, you have to sell a lot of that drug. The more patients you can sell to, the more you sell. The more conditions that your drug is approved to treat, the more patients you can sell to, and thus the more money you make, and the more individuals you expose to the potential side effects of your drug. Maybe that's why every few years the sponsor of Cymbalta had a few more clinical trials ready for a new condition. I'd love to go into each and every one of these use cases for Cymbalta, but this video would never end. Let's keep it focused on the original NDA, when Cymbalta was approved to be no more than a mere antidepressant. Let's see what the label says. It starts with, Cymbalta is a selective serotonin and norepinephrine reuptake inhibitor. These are mostly words we've heard before. You can already get an idea of how this drug is supposed to work. It's based off of the monoamine hypothesis. Serotonin and norepinephrine are both monoamines. Since Cymbalta is supposed to inhibit their reuptake, that means it stops these monoamines from being removed from the synapse, thus increasing the levels of these monoamines in the synapse. But how does it do all that? Let's read on. The mechanism of the antidepressant action of duloxetine in humans, duloxetine being just another name for Cymbalta, is unknown. I guess we're on our own to figure this one out. When you swallow a pill, it goes through your lips, down your throat, through the esophagus and into the acid lake of your stomach, where food gets digested. With Cymbalta, this is a problem. Diloxidin, the chemical name for Cymbalta, is very unstable in acid, and when placed in an acidic environment, much of it is converted into a substance called 1-naphthol. 1-naphthol is extremely toxic, producing cramping, abdominal pain, nausea, vomiting, and in severe cases, nephritis, cystitis, liver damage, and convulsions. This is why diloxidin is delivered in little pellets with outer coatings that are resistant to acid. So hopefully the coating on the pellets keeps the diloxidin from turning into poison in your guts long enough for it to get to the next stage, in which the stomach passes off the drug to the small intestine. This is where most drugs, including diloxidin, get into the bloodstream. The drug can pass through the walls of the intestine to get into the bloodstream, but not without passing through some hurdles first. Note that the small intestine is the opposite of acidic. It's alkaline. Alkaline environments chew through the acid shield of the diloxidin pretty well, exposing diloxidin to the walls of the intestine. The walls of the small intestine will metabolize some of the drug and then send it out to the bloodstream, where it will have to face the biggest, baddest metabolizer of them all, the liver. It is only after being metabolized by the liver that the drug is sent throughout the rest of the bloodstream. What does it mean for a drug to be metabolized, though? Your body is very smart, and when a chemical passes through your body that your body doesn't recognize, it will break it down or change its form in a way that will hopefully prevent it from causing any harm. This is mostly done by the liver, but other parts of your body have the ability to metabolize drugs as well. The changed substances that come out of the act of metabolism are called metabolites. In most cases, your body is successful, and the metabolites will be less chemically active than the original chemical, passing through your bloodstream, attaching to nothing, therefore doing nothing, until it gets passed out of your body through urine, for example. However, your liver isn't perfect. It may be the product of millions of years of evolution, but it doesn't know how to stop everything. In some cases, the metabolites will be just as chemically active as the original chemical, or even possibly more chemically active, and thus more dangerous. The fact that your body takes drugs and makes its own changes to them is a major issue in drug development. Cymbalta is a victim of this. Studies indicate that around 80% of a dose is converted into metabolites. The ones that have been identified can be seen in this chart here. This is probably not the full list. To me, this is worrisome. Let's look at one of the sponsors' studies of Cymbalta metabolites in 4 healthy volunteers, a study labeled SAAZ. To find the metabolites, they gave volunteers the drug and then measured what came out in their urine and feces. They can identify the drug by attaching radioactive atoms to the drug molecules before the drug is ingested. Thankfully, no 1-naphthol was recovered in this study,
although it was in study HBAF. What is worrisome is that around 5% of the drug recovered in urine and 12% of the drug recovered in feces was in the form of unidentified metabolites. Metabolites not included in that little chart earlier that can be almost anything, even an epoxide. The study showed that around 6.6% of the dose given appeared to be broken down by an epoxide, or rather, the drug was eating itself by turning part of itself into an epoxide, which then goes on to break down more of the drug. Epoxides are highly reactive chemicals which make them dangerous to the human body, especially the liver. The sponsor says that there's no risk of this being the case, as no epoxides were found circulating in the bloodstream in the study. But the researchers disagree with the sponsor, saying that it is likely that an epoxide of this kind could avoid detection in an experiment like this. The sponsor is quick to dismiss many claims of toxicity in these studies. It's almost as though they invested billions of dollars into this drug and don't want to see it left unapproved for human use. So we left off at the liver. The small intestine and liver have broken down and changed much of the duloxetine, but some will be left intact. The drug and its metabolites are then sent off into the bloodstream. The bloodstream carries these chemicals all throughout the body, into and out of tissues and organs. This is the main cause of drug side effects. Once a drug is in your bloodstream, it goes everywhere, and there are few ways to stop that. The only place in your body that's off limits to most chemicals is the brain and the spinal cord, due to a system called the blood-brain barrier. The blood-brain barrier is basically a wall between your bloodstream and brain with guards that only let certain substances in. This is very important. As delicate and complex as your body from the neck down is, your brain is even more delicate and more complex than that. If anything was allowed to get in there and mess with the wiring, it could potentially wreak havoc. Duloxetine is able to cross this blood-brain barrier. All antidepressants can. So what happens once duloxetine gets in your brain? It inhibits serotonin and norepinephrine reuptake pumps. At least, that's the idea. Recall that serotonin and norepinephrine are both monoamines that neurons fire at each other in order to cause changes in the brain. Eventually, these monoamines have to be cleaned up so that their effects can be effectively turned off. One way this happens is that special proteins, referred to as pumps, take these monoamines out of the synapse and back into the neuron to be recycled. In lab tests outside of the human brain, we see that duloxetine is able to bind to these protein pumps that recycle serotonin and norepinephrine, making them useless. Disabling the pumps should keep more serotonin and norepinephrine floating around in synapses. Let's see how the mechanism of action is described in the FDA's pharmacological review. Mechanism of action. The mechanism of action of duloxetine as an antidepressant is unknown. As for other currently approved antidepressants, the actual mechanism of action is probably through, as yet unidentified/unexplained, compensatory mechanisms initiated by the direct effects of the drugs. For duloxetine, the initiating effect is assumed to be blockade of reuptake of serotonin and norepinephrine, which results in enhanced serotonergic and noradrenergic
activities in the central nervous system. What they mean by this is that the initial effect of duloxetine is assumed to be the binding of duloxetine to serotonin and norepinephrine protein pumps. This is assumed because we can't see what happens in real time in a living human brain. We can only make assumptions based on lab tests. Anyway, duloxetine binds to serotonin and norepinephrine pumps that are responsible for getting rid of serotonin and norepinephrine in the synapses, in theory. But you'll notice they don't even say that that's what cures depression. They attribute it to the compensatory mechanisms as a result of this effect. The compensatory mechanisms being the actions that your brain takes to restore the balance of chemicals in your head after you alter it with the drugs. You see, your brain generally doesn't like to change. When you start flooding your synapses with serotonin and norepinephrine, the brain does something to try and maintain order. Perhaps it slows down the production of serotonin and norepinephrine, but as stated in this review, we don't really know what the brain does to restore the balance. But does it all work? Though antidepressants aren't well understood, not many drugs are, but many poorly understood drugs still do a lot of good. Is there still a case for taking antidepressants? The label tells us that the efficacy of Cymbalta as a treatment for depression was established in 4 randomized, double-blind, placebo-controlled, fixed-dose studies in adult outpatients meeting the DSM-4 criteria for major depression. Fixed dose meaning the amount of drug given to a treatment group won't change during the study. Placebo-controlled, meaning at least one treatment group will not be given the drug, and instead will be given a placebo. Double-blind, meaning each patient doesn't know if they're being given the placebo or the actual drug, and each investigator doesn't know which patients are on the placebo and which patients are on the actual drug. Randomized, meaning that each patient is assigned to a treatment group randomly, not based on any criteria such as age, gender, severity of depression, and so on. It's probably no surprise to you that I have a few issues with these studies. First off, what do you use to measure the depression levels of each treatment group in order to be able to tell if the drug is measurably making patients feel better? To tell if the drug is working, at specified time intervals, each patient is assigned to a number using the 17-item Hamilton Depression Rating Scale, aka the HAMD-17. Which I will refer to from now on as the HAMD-17. There is absolutely nothing scientific about the HAMD-17. It's a list of 17 multiple choice questions. Things like, are you depressed? Are you feeling guilty, suicidal, having trouble sleeping? Answers that a depressed person would give get high numbers, and answers that a non-depressed person would give get low numbers. The idea is that the lower your number, the less depressed you are, on a scale from 0 to 53. Basically the equivalent of some sort of corny internet-hosted "Are You Depressed?" quiz. In clinical trials, this form is filled out for each patient at regular intervals by the investigators after they interview the patients. You heard me right. The investigators that are hired and paid for by the sponsor to conduct these clinical trials are in charge of judging who is feeling better and who is not. Do you see the conflict of interest here? Who's to say that the drug sponsors aren't paying off the investigators to give less depressed ratings to patients taking the sponsor's drug? You might be thinking, that's the point of the double-blind study. Both the investigators and patients don't know who's taking what pill. If that's the case, there's no way that the investigators can try to manipulate the HAM-17 ratings to mess with the results. But you forget, all drugs have side effects. In the case of Cymbalta, some pretty major ones ranging from nausea, dry mouth, appetite and weight decrease, dizziness, tremors, hot flushes, blurry vision, insomnia, abnormal orgasms, etc. You don't generally feel these things after taking a sugar pill. These side effects will be apparent and monitored by the investigators. So in practice, the question of who's on the drug and who's on the placebo is no real secret to the investigators. Let's check the FDA compiled statistical review of the sponsor's NDA to read more about these clinical trials. All 4 of the studies mentioned on the label are here and reviewed by a statistician of the FDA. Also included are a couple more failed studies that don't show significant difference between the drug and placebo. The studies are all very similar, so for the sake of this presentation, we will focus on the one that I feel deserves the most attention. A study labeled F1JMCHMBHB. A total of 367 people signed up for this study. For reasons not outlined anywhere in the documents, 100 of these people did not meet the criteria to enroll in the study or change their mind about participating, leaving 267 patients in the study. Let's go into speculation land here for a little bit. I've learned many important lessons from a man named Dr. Peter Breggin. He's an American psychiatrist who has been a major activist against what he sees as harmful psychiatric practices. For decades, he's been an outspoken critic of psychiatric medication. He's been invited many times to testify before federal agencies and U.S. Congress as an expert on the adverse effects of psychiatric drugs. In his time spent investigating dishonest drug companies, he's noticed a common practice in these clinical trials called placebo washout. Basically, in the screening phase, everyone who's signed up to participate will be put on a placebo before actually starting the clinical trial. Any patients who start to feel significantly better after taking this placebo are then excluded from the study, perhaps under the assumption that they're not depressed enough to be eligible for treatment if a sugar pill is able to cure their depression. Regardless, there's no denying that practices like this add bias in favor of the drug to the data. So there are 267 patients in the trial. Each patient gets randomly assigned to one of 2 treatment groups. One group of 139 patients is to be given the placebo pill once daily. The other group of 128 patients is to be given a 60 milligram dose of Cymbalta daily. These patients will be monitored for 9 weeks only. They are assessed using the HAM-17 assessment at the beginning of the study and at the end of the study. If the HAM-17 numbers are significantly lower for the Cymbalta taking group versus the placebo taking group at the end versus the beginning, then the drug is shown to be effective in the eyes of the FDA. Something of note, in this study, 35.3% of the patients in the placebo group and 39.1% of the patients in the Cymbalta group didn't finish. They dropped out of the trial, and the reasons why are as interesting as they are vague. This first one, lack of efficacy, if the patient or any of the investigators overseeing the trial felt that a patient wasn't getting better, that patient could be dropped from the trial. Each time this is an investigator's choice, there's a potential source of data manipulation. But let's get out of conspiracy theory land. Data manipulation or not, here are the results of the trial. There are two ways that the results were analyzed that largely only differ in the way they handle missing data. That missing data being the result of some patients dropping out of the trial. Using one method, they determined that the patients from the Cymbalta group, on average, had a HAM-17 score fall by 10.46 points. Sounds pretty good, until you see that the group taking the sugar pill had a drop of 8.29 points. Using a different style of statistical analysis, the Cymbalta group had a drop of 8.75 points on average, compared to 7.02 points in the placebo group. In both assessments, the difference between the average fall in placebo versus Cymbalta groups is about 2 points on the HAM-17 scale. Look at the HAM-17 and think about it. This 2-point difference could be the difference between compulsive hair playing and compulsive hair pulling. But this is all that it takes for the trial to be statistically significant in favor of Cymbalta. In every single trial outlined in the statistical review, the differences between improvements are so small between placebo and Cymbalta that I can't believe any reasonable human being could come to the conclusion that the drug is effective. The only thing that could come to that conclusion are the mathematical models used for statistical analysis that could only be close to accurate if a bunch of unreasonable assumptions about the data are made. But wait, just wait. I have saved the worst crime against statistics for last. The sponsor realized midway through the study that the enrollment rate in this study was kind of low, but the enrollment rate in another study running at the same time was kind of high. In order to correct this, the sponsor took patient data from the other study and brought it into this one. That, I believe, is one of the greatest sins that you can commit as a statistician. It could very well be the case that one trial was looking very, very good for Cymbalta, and the other trial was looking mildly bad. If you take a group of patients with positive Cymbalta reactions from the good trial and put them into the bad trial, it's possible to make both trials look mildly good for Cymbalta. Better to have two mildly successful trials as opposed to one successful and one failed trial in the eyes of the FDA. The FDA met internally to discuss the plan to shift the patients, but was unable to provide feedback to the sponsor before the implementation. Sounds a little bit like special treatment to me. So here we have a drug that's barely better than a sugar pill in terms of treating depression. Its effectiveness has been established in only 4 9-week studies, subject to potential and explicit data manipulation. The drug breaks down into understudied and even unknown metabolites doing unknown things inside of your body. It has the potential to cause liver damage, negative effects on blood pressure, mania, seizures, suicide, and that's only what they're willing to admit. And then there's the issue of withdrawal, or as the label calls it, discontinuation symptoms. Note that the label is not too keen on throwing around the W word. Apparently, upon abrupt discontinuation of the drug after only 9 weeks, a good proportion of the patients stopping the drug experience dizziness, nausea, headaches, paresthesia, vomiting, irritability, and even nightmares. Nightmares. That's how deep in your head this stuff gets. It can even haunt you in your dreams. These withdrawal effects are not surprising. Your brain has most likely made long-term changes to its structure to account for its synapses being flooded with serotonin and norepinephrine. The label says that this is how the drug works, after all. When you take away the source of that flooding, the effects of these long-term changes now have to be undone. Unfortunately, this can be quite an uncomfortable experience. You can hear it echoed in many testimonials from former users of Cymbalta.
I was diagnosed in 2008 with primary fibromyalgia. I had a lot of pain, I had a lot of back problems also. So in 2009, my physician wanted me to consider a fibromyalgia program in my area with a neurologist. And so this program was 6 weeks in which they start you on Cymbalta.
I've been dealing with anxiety and depression for a while. I would say since high school, and it's always been a cycle. I don't want to get out of bed. I don't want to talk to anyone. I completely shut down and isolate myself, and it messes up my work performance. It messes up my relationships with people, and I basically just sabotage myself. So this time, it was really, really severe, to where I actually went to a doctor to seek medical professional help because I didn't know what to do. My doctor prescribed me this drug called Cymbalta.
I've been taking Cymbalta for 6 months. I was told that I would have to be on it for 6 months in combination with another drug to treat my major depression.
I always knew that it was mental health that kind of was sometimes the breakdown of my relationships. Because this relationship was so good and I was really committed and stuff, and I thought, you know what, I'm going to do something. I need a change. I want to make this relationship work, and I'm not going to let my mental health get in the way. So I decided to start therapy at the same time as take medication. Oh, and also I had lived with chronic pain for 6 years. In the end, he gave me duloxetine, Cymbalta. I'm guessing he thought this was kind of two birds with one stone. It will get rid of my anxiety and depression and also my chronic pain.
And immediately I noticed that I was experiencing really nasty side effects. So I noticed that I had a lot more anxiety, that my fibromyalgia pain did not get diminished. I still was in pain. I still had a lot of inflammation and backaches and just muscles hurting all over. I felt like there was really major changes happening that turned my life upside down as far as the mental health aspect. I couldn't get out of bed. I had depression that was so severe, I just felt suicidal. And I knew that something was wrong.
You know, I asked the doctor, I asked the nurse, and I asked the pharmacist, and all three of them told me, oh no, there's no side effects. You might get sleepy, so make sure you take it before bed. Sometimes you get a little bit irritable, you'll get a little agitated, but that's about it.
Cymbalta destroyed my memory. I had to use I had to use GPS to get around the city I lived in because I couldn't remember how to get places, and that was really terrifying for me. The fact that I couldn't remember my own birthday at one point, I mean, things were getting pretty rough.
Then next thing I know, I wake up it was probably 1 in the morning, 2 in the morning, and my legs were just so restless, almost like I was going through opiate withdrawals. It felt like they were on fire.
He didn't tell me that there would be any side effects. He said, you might have a couple of side effects when you begin, but nothing too bad. I didn't sleep for maybe a month. I sleep really well. I know a lot of people with mental health suffer with sleeping, but I'm really lucky in that like my head hits the pillow and I'm out for the night. I just couldn't sleep. I was tired, my eyes were tired, my body was tired, my mind was tired, but my body wouldn't sleep.
I, finished that and then went back into school, and it was kind of miserable trying to remember things that, were vital to what I needed for my degree. on top of stupid things like, how do I get back home from here? Or how do I get to a store that I've gone to a million times in my past?
Usually when I have work the next day and I can't sleep, I get like a little bit, not angry, but upset, because I'm like, damn, I need to get my sleep. This sucks. I'm going to be all tired tomorrow. But I didn't feel any of that. I got probably 2 hours of sleep that night, but I was able to jump right out of bed, and I had a bunch of energy, and I seemed to be in a pretty good mood, but it was kind of like blurry. Like I felt okay, but it was like I was like not necessarily sleepwalking, almost like I was on like if you were to mix like a small dose of Xanax and like a beer.
And I've had people, for the most part, here that I was taking it, and they thought, wow. And they would tell me, wow, you know, when I took that, I felt like a zombie, and it turned me into a totally different person. I didn't have that. I don't think I had that.
I went out and I sat in my car, and I swear I sat there for 30 minutes. And I was thinking, it's weird because all these thoughts were going through my mind, but I didn't feel like I was in my head, if that makes any sense. Because sometimes when we overthink things, we tend to get anxious and we get overwhelmed, and we start kind of working ourselves up. And I didn't feel that way. I just kind of felt like a zombie, and I just kind of felt like paralyzed. Like I was just sitting there kind of like this for like 30 minutes, just staring at the ground.
And when I did sleep, I would wake up and my jaw would be locked because I'd been grinding my teeth so much, which I've never ever done in my life. So I'd been grinding my teeth so much, and I was in so much pain. Again, I researched it. This is another side effect of taking Cymbalta. Yeah, I don't remember a lot around that time because it just made me feel very foggy.
I would really have to think about the name of the man I live with in this house. I couldn't remember his name. I mean, that's a big deal.
So I went to my neurologist, and at an appointment, I told her what was going on and said, you know, hey, I gave it 4 months, but I don't think this is working for me. And could you just please taper me slowly off this drug? And instead of helping me, she dismissed me as her patient. So I was pretty much left to wing it on my own.
Now, let me tell you, there has been class action lawsuits against Lilly Eli, which is a drug, Cymbalta's drug company, because they did not originally warn people of the severe withdrawal symptoms. And I mean severe withdrawal symptoms, like so severe that some people went into psychosis.
So your doctor may not, maybe they'll tell you about withdrawals. No one told me about withdrawals. Not one doctor told me that I could go through horrific, hellish withdrawals.
Missing a dose put me in the most miserable pain ever. It was far worse than flare pain before taking Cymbalta. It was horrible. And then coming off of Cymbalta was like that every day for almost 2 months.
I had a really busy time. I graduated and I was living in London, and I was in a show, and I was having loads of rehearsals, and I was a dog sitter as well, and I was just all over the place for like a week and a half, and I thought I had more pills and I hadn't picked them up. I hadn't picked up my Deluxetine medication, and so I was like, oh, okay, well, I'll have to just, I only had like 4 left, so I was like, okay, I'm gonna have to have like one every couple of days or something, and then just for the other half of a week I'm just gonna have to get through it because I did not have time to go.
So what your doctor may not tell you in advance is that maybe he or she doesn't have training on how to gently, safely wean you off this drug. And many doctors, they go on board, they're so willing to write that prescription, but when it comes time for the patient who says, hey, it's not working, and oh my gosh, I'm having so many problems and negative side effects, and they want to stop, and then the doctor says, no, we want you on the drug indefinitely. No, we will not help you stop. This puts us in a really bad, dark, unsafe place, and which I myself found myself in a dead end. I didn't know what to do.
I'm going to keep on dropping it until I'm completely off. And I'm doing this without the help of my doctor, but I am under supervision of a doctor. I have a psychiatrist that I see about every month for like the last 6 months. But yeah, she didn't really want me. I asked her about taking me off the medication, and she didn't really want me to come off the medication, it seemed like. But she wasn't my original doctor. My original doctor told me that I only had to be on it for 6 months. And she's telling me that I have to be on my whole life. I'm going with what the first doctor said, 6 months. I'm not staying on drugs my whole life. Because these drugs are very powerful, and they do all kinds of things to your body. And this is a newer drug too. So I'm sure there are things that we don't even know about that this drug can do to us. After taking it for a prolonged period of time.
I didn't know, obviously I was never told about that you get really bad withdrawal symptoms from Cymbalta, and this is how I found out. Unluckily, like, I basically went cold turkey, and I thought I was really, really unwell. I didn't think, I just thought my body was like breaking down and quitting on me, because hang on, I've written them all down so I don't miss any. So brain zaps were the worst thing. I'd never heard of them before, but it's like a huge bolt of electricity just zipping through your brain, and you can get them for like 5 minutes at a time, or just one, or it will last for hours, and it is hell on earth. It's not like a migraine. It's just like a bolt of electricity, and all I could explain it as was a brain zap. And then I googled it, and it was actually, it's what a lot of people call them, like brain zaps.
The only thing I've been having is nausea and a little bit of like little brain zaps. I get like this electricity in my head. Brain zaps. I know it sounds weird, but that's what it is.
My own new doctor, so I found a new doctor, and he said to slowly taper Cymbalta by opening up the capsule and just counting beads. I have to say that I was a little bit surprised that a board certified doctor is going to tell me to open up a capsule and start taking it apart and counting beads. I feel that was not exactly the solution I was looking for. Number one, if you're in physical pain. Number two, if you have brain fog. If you're in depression, you have anxiety, you have insomnia, you're not functioning at your best, it's not always a good idea to take apart your capsule.
They come in capsules. They don't do them in tablets, which is the most ridiculous thing I've ever heard, because of what I'm about to tell you. You can't cut these in half. You can with tablets. So yeah, that's how they come, in little capsules with hundreds of little beads inside of them. They've had to open up their capsules and go down a couple of beads a day, or a bead a day, until they come off of it. Let me show you how many beads are in here. Actually, I don't know if you'll be able to see. Oh, just dropped them. So that's how many beads there are. There are more than that, because I just dropped about 50. But yeah, so I went down, first of all I halved them, and then went down by 2 each day. Me and my mum did some research, and we both saw that a lot of people that have been in exactly the same situation as me took down like a bead at a time, and that's what I've been doing. So in 7 days I should be off duloxetine, so I'm going to keep you guys updated. I'm excited. I'm really excited to have it out of my system and to be able to say that I'm not on this medication anymore.
So here it is, 2017. I am so thankful and grateful that I A, survived, B, got through it, and C, I'm beyond the bad withdrawals. So, you know, there is hope. I'm here to say there is hope for those who are right now smack center in a wicked withdrawal, or the horrific symptoms that are part of Cymbalta.
Flies are bad today. All right, we're rolling. I believe in the right to try. I cannot prove to you that antidepressants will not work for you, but if you have been taking one or more antidepressants for a length of time greater than 9 weeks, I believe that you are putting your mind at serious risk. The American healthcare system has a problem with transparency. What I found most astounding during my research is that it's impossible to find the raw data that the results of these clinical trials are based on. So many of the FOIA documents that the FDA literally has to make available are severely redacted. And if a clinical trial goes bad, drug companies have the right to withhold publication of that data. Until the issue of transparency can be addressed and more research is done on the mechanism of action of antidepressants, the use of antidepressants should be considered high risk. If anything, only used as a last resort treatment option for the most depressed among us, who should then be closely monitored, as their suicide risk may actually increase as a result of taking antidepressants. If you feel similarly and would like to get off psychiatric medication, I suggest you follow the advice of Dr. Peter Breggin as outlined in the Antidepressant Fact Book. Take a minute here. Antidepressant Fact Book by Dr. Peter Breggin. Turn to page 131, and I want to leave you with 10 principles. Well, I'm not going to give you all 10, but his principles for withdrawing from psychiatric drugs. First, especially if you have been taking large doses for a long time, find an experienced professional to help you go through the withdrawal process. Of course, easier said than done, but ideally, that's what you're going to want to have. If you experience serious emotional problems before you started taking the drug, be sure to get psychological help before, during, and after the withdrawal process. It's unfortunate that a lot of people going through psychiatric drug withdrawal happen to be the ones that are truly like emotionally damaged, people that really need help and have the most at stake for being in a state of mind like that. You should tell close family members or friends that you're withdrawing from a psychoactive drug. Explain that withdrawing from antidepressants can cause depression or mania. Ask them to tell you if you start to behave in a manner that's at all worrisome or alarming. You want others to be watching over you because it's often difficult to be objective about your own behavior during drug withdrawal. Unless you are having a serious adverse drug reaction that requires withdrawing more quickly, go slower than you think you need to. A good rule of thumb is to lower the drug dose no faster than 10% each week for 10 weeks. Don't believe your medical doctor if he or she claims that antidepressants don't cause withdrawal problems. Many doctors are ignorant about antidepressant withdrawal reactions. If you start to have what seems like a serious withdrawal reaction, immediately consult with a professional who has clinical experience. At the same time, you might ask your doctor about resuming your previous dose, at least temporarily, in the case of, some of these withdrawal reactions can be very severe. If you are trying to withdraw from several psychiatric drugs, it's generally best to withdraw from one at a time. Withdrawing from 2 or more drugs at once can be confusing. If you begin to have a withdrawal reaction, you may not be able to figure out which drug is the culprit. And there's a couple others, but that pretty much sums it up. On a final note, to all of my viewers who may be struggling with depression, I hope that each of you find your individual answers and go on to live peaceful and fulfilling lives. Thank you.